So today we shall continue our discussion on the transmission of particles through a barrier, also known as tunneling. So we have a potential barrier and we have a particle with energy E incident on it from the left side, and classically the particle would go up to the point A and then turn back. In quantum mechanics we find that there is a finite probability of finding the particle on the other side, because on the left hand side the wave function of the incident particle is an oscillating function. The amplitude remains constant. Once it enters the region where the energy is less than the potential, it becomes an exponential function, the wave function, and once it reaches the place where the energy is again equal to the potential and larger, the function again emerges as an oscillating function. And if you match the boundary conditions, you find that there is a part of the oscillating function which comes out onto this side. And we had worked this out in detail for the step potential, where the potential was a constant, and now we are considering a situation where the potential has some arbitrary form. And I told you that the left hand side you can apply the WKB solution, on the right hand side also you can apply the WKB solution, and in the central regions also where the energy is less than the potential, you have the WKB solutions. These solutions do not hold near the classical turning points. You have to continue these solutions, you have to connect these solutions across the classical turning points, and we saw that one can relate these solutions through the classical turning points, and we had discussed the relation in this situation in the last class, and using this we had calculated the transmission coefficient, and the transmission coefficient turned out to be this. So the transmission coefficient was expressed in terms of a variable theta, where theta is the integral from A to B. So A and B are the classical turning points. Rho is the integral of, is the square root of 2m v minus E by h cross squared. So you have to integrate this quantity from between the two classical turning points. This without the factor of 2 is theta, and without the minus sign also this is theta, and 1 by theta squared is minus 2 into this whole thing exponential. So when theta is large, the transmission coefficient turns out to be this, and for all values of theta the transmission coefficient is equal to this. Okay, so this is what we had done in the last class. Let us now apply this to a particular problem and see how the transmission coefficient actually depends on various physical parameters. So we are going to consider a problem where we have a nucleus. So we have an atom, and the atom, as we know, has a nucleus. So this is actually a three-dimensional problem, but we are going to study an equivalent one-dimensional problem, and the basic results which we obtain here also hold in the three-dimensional situation. In the three-dimensional problem, the spherical symmetry holds, and it is effectively a one-dimensional problem. Okay. So the situation is as follows: there is a nucleus over here, and the nucleus has got charge, let us say Z2. It has got Z2 protons, so the charge is Z2 into E, and this will produce an electrostatic potential which will fall off as 1 by R, and let me plot the potential here. So the potential is 1 by R. So if I am bombarding a positively charged particle, let us say an alpha particle, onto this nucleus, then that alpha particle as it approaches the nucleus will experience this electrostatic potential. It has to overcome this potential if it has to go and hit the nucleus, and the potential will be Z1, Z2, where Z1 is the number of protons in the incident particle. For an alpha particle it is 2, E is the charge of the electron or the proton, this divided by R. We are choosing units where the factor of 1 by 4 pi epsilon does not appear. If you want to keep that, then you will have, okay, let us use that also. So this is in the SI units. So this is the potential. So a particle incident from this side will experience this kind of a potential. And this, you should remember that this is actually a 3-dimensional problem, and from, if you apply spherical symmetry, then you can reduce it to a problem of only the radial coordinate r, and here r goes from minus infinity to 0. We consider an equivalent 1-dimensional problem where x goes from minus infinity to 0. Okay, we are not dealing with r, but x goes from minus infinity to 0. You have a similar kind of potential on this side also. And there is a particle with energy E incident on this. So this is the energy of the particle which is incident on this. So the classical turning point, classically the particle would only be able to approach to a distance a where the kinetic energy, where the total energy of the particle would be equal to the potential energy. So the kinetic energy would be 0, particle would come to rest and then again go back. So the particle would approach, come to rest here and then go back. Now we want to study the phenomena where, suppose we send in some alpha particle onto a nucleus. Classically the alpha particle would come back here and go back. In a quantum situation, the alpha particle, there is a probability that the alpha particle will penetrate this potential. Now if you approach the nucleus to within the nuclear distances of around 1 Fermi, then the potential again becomes attractive. Here the potential is repulsive because the only interaction here is the electrostatic repulsion between the two positive charges. But if the incident particle can overcome this repulsive potential and get within the nuclear, in the range where the nuclear forces start acting, which is inside the nucleus. So if the particle can overcome this potential and get somewhere very close to the origin, then the nuclear forces start acting and the nuclear forces are attractive. So if the particle can somehow manage to get here to very small distance from the nuclei, then the nuclear forces start acting, and those forces are attractive, and those forces, the potential, the nuclear potential is actually larger than the electrostatic repulsion at very small distances. So if it can overcome this potential and get inside, then it can get bound to the nucleus and you can have a larger nuclei. Or it may so happen that the alpha particle may form a part of that large existing nuclei and then the whole thing may disintegrate. So we want to see what is the tunneling probability or the transmission coefficient for this incident particle to go through this potential barrier to r equal to 0, which we should understand as the particle overcoming this electrostatic repulsion and going into the range where the nuclear attraction starts working. So then it can become a part of that nucleus. So it starts experiencing the nuclear attraction there and it may form one bound nuclei. Okay. So this is the situation we are considering. So we want to calculate the transmission coefficient from a to 0. Once it can reach 0 or some very small length scale, which we can treat as 0 effectively, the incident particle has gone and merged into the nucleus and the nuclear attraction will hold it there. Okay. So we want to calculate this transmission coefficient. So the transmission coefficient is 1 by theta squared, which is what I just wrote down, where theta is exponential in this case okay, exponential the integral a to 0 the integral rho x dx. So, what is rho? Rho is 2m by h cross square Vx minus E, this whole thing square root into dx.
So for this we have assumed that theta is very large, so is that valid?
Right, it is valid.
0 to is very small.
Yeah, let us calculate theta and then we can see what is the transmission. Right, let us first calculate theta. Okay. So we are going to first calculate theta. So in order to calculate theta, we have to first evaluate this integral. So let us do this integral. So the integral we wish to do is 0 to a square root of 2m by h cross square, and then I have z1 z2 z1 z, sorry, it should be, the integral should be a to 0 z1 z2 by 4 pi epsilon x z1 z2 e squared by 4 pi epsilon x minus e into dx. Okay. And the classical, let us also determine the classical turning point. The classical turning point is the point A is the point where the energy is equal to this potential. So the classical turning point is where z1 z2 e square by 4 pi epsilon a is minus e is equal to 0. Well, we should keep in mind the fact that we are looking for the negative solution over here. We are looking for the negative solution. There will be two such classical turning points, and the potential is 1 by the mod of x. Okay. So this is actually the mod of x which comes in here, and x is, so this is actually, okay, minus, right, because x is negative and the potential is positive. So minus this is equal to this which implies that A is equal to minus minus z1 z2 e square by 4 pi epsilon naught into E. Okay, so we have determined A, the classical turning point. So this integral now becomes A to 0 square root of 2m. I can take the E common outside, E by h cross square, and I now have minus, this whole thing is A, so I have, okay, A by x, because the minus sign also gets absorbed into this, minus 1 dx. Okay, so this is what we get. Now, Let us also define, okay, a by x to be equal to, or rather x by a to be equal to some u have we got the signs? Let us just check if we have got the signs correct throughout. So there was a minus sign here, and a also has a minus sign, so there's a overall minus sign here. Okay. So this is what we have. Okay, let us define this to be by mod of a, or no, let us see how. Okay. Okay, let us so we have this, so this becomes equal to, I can take this whole factor outside, 2me by h cross squared square root of 1 by u minus u, and this becomes du, and I get a factor of a outside, because dx is equal to a into du. Okay. So let us now evaluate this integral. So this is equal to square root of 2me by h cross square a, and here I have 1 to 0, the limits get changed from 1 to 0, 1 to 0 square root of 1 by u minus u du. Okay. So let me first evaluate this integral over here. So the integral over here is, so we want to first evaluate the integral 1 to 0 1 by u minus 1 du. So this is very simple, you just define u to be sine square theta. If u is sine square theta, then du is 2 sine theta cos theta d theta, and this integral becomes pi by 2 to 0. This is equal to pi by 2 to 0, and on top I have, on the numerator I have 1 minus sine square theta, which is cos theta. So this becomes cos theta by sine theta, the numerator is sine theta, and I have 2 cos theta sine theta d theta, this is the du, and this gives me minus 0 to pi by 2 cos square theta d theta, which we know is equal to minus 0 to pi by 2, this is cos 2 theta cos 2 theta plus 1 by 2 d theta, and the first integral from 0 to pi by 2 gives us 0, the second integral gives us minus pi by 4. Okay, so we have evaluated this integral.
So you have Mr. 2, you have Mr. 2.
Right, there is a factor of 2 which comes in here, and there is a factor of 2 which comes in here and here. So this gives us minus pi by 2. Thank you. So the final result is minus pi by 2. So let us use this now let us use this in the integral which we were evaluating earlier. So this is a side step. So using this, we find that the integral a to 0 rho x dx. This is the integral which you are evaluating, and this turned out to be square root of 2m e by h cross squared into a. So what is a? A is minus z1 z2 e square by 4 pi epsilon naught e. So this is a into the integral which we just evaluated, which is minus pi by 2. Minus pi by 2. So we have this integral finally. So let us so what is this integral now? The integral, so this e will cancel with the e over here. So what I have here is square root of 2m by e h cross square into z1 z2 e square by 4 pi epsilon naught into we can leave this pi over here, okay, pi by 2. So how much is 2m by e for the particle? For a free particle, where the potential is 0, we have half m v square is equal to e, or v is equal to two e by m square root. So this is equal to let us convert this to the factor which we have. So this is equal to e by 2m into 2 outside. So square root of 2m by e is equal to 2 by v, right. So this factor over here two m by e h cross square becomes equal to, so there's a factor of 2 which comes in over here. So this 2 over here will cancel with the 2 over here, and what I have is 1 by h cross square into v. Yeah, there's a square root, right? So 1 by hv. So I can put this whole thing here. So I have z1 z2 e square by 4 pi epsilon, this factor of 4 pi epsilon, and then I have h cross v, and here I have a pi. Okay, so we have evaluated the integral, and let us now use this to calculate the transmission coefficient. That is what we set out to calculate. So the transmission coefficient turns out to be exponential minus 2 exponential z1 z2 into e square pi by 4 pi epsilon naught into h cross into v. Okay, so let us now, so what have we obtained? So suppose we have a particle with energy E. such that when the particle is far away from the nucleus, the particle is incident on a nucleus, it is being bombarded onto a nucleus over here. When the particle is far away from the nucleus, far away from the electrostatic force, where the electrostatic potential becomes negligible, if the particle has a velocity speed v, if such a particle is incident on this nucleus, then the transmission coefficient is given by this factor over here. Okay. So this tells us the effect of the electrostatic potential on the nuclear reaction. So what is the situation? I have a nuclei here and I am bombarding, let us say, an alpha particle. The alpha particle has to overcome this potential to get here, to get to this nucleus. And the only way it can do that is to tunnel through this potential to get here. So the larger the charges of this particle, the larger the charge of this particle or the incident particle, the less is the probability of it getting to this nucleus. Okay. This is the only factor which comes in. The other factor which comes in is that the higher the energy of the incident particle, the smaller this number is going to be. So more is the transmission coefficient goes up. So the probability of this incident particle going and hitting this nucleus, going within the nuclear interaction range, that goes up if the incident energy is higher. Okay, this factor over here is also known as the Gamow factor. So what is the effect of this factor? So if I have a nucleus and I am bombarding some particle, so this is Z1, and if you calculate the nuclear reaction rate or some quantity like that, taking into account the nuclear interaction, then the actual reaction rate will get reduced by this factor. Because if I have a flux of incident particle, only this fraction of the incident particle will get through to this nuclei. The rest of them will get reflected back. Right? This is what the transmission coefficient tells us. It tells us what fraction of the incident flux of particles will actually tunnel through to this nuclei. For this particle to get here, it has to tunnel through. From some region here to here, it has to tunnel. Classically, there is no way it can get through. And the fact that it has to tunnel has gone into this. So whatever reaction rate you calculate using just the nuclear reaction interactions, the actual rate is going to be reduced by this Gamow factor, which accounts for the fact that the particle has to actually tunnel and overcome this electrostatic repulsive force. This Gamow factor also comes in if you study the alpha decay of particles. In alpha decay, again, a particle has to tunnel out. In the alpha decay, the situation is the reverse of this. You have an alpha particle already in the nucleus, and it is bound in this nucleus by the nuclear interaction, which is trying to keep it in. And then there is a potential. If it can overcome that potential and get out, the electrostatic repulsion will again push it out. So the tunneling out of alpha particles is also governed by this factor comes in over there also. Okay. For example, if you are considering the reaction where two protons, so I have a proton and I have a proton, two protons can combine to give you, can combine to form a nuclei, right, which will be helium, some isotope of helium. A proton can also combine with a neutron to give deuterium. right? This will be helium, some isotope of helium, this will be deuterium. Now the nuclear interaction, as far as the nuclear interaction is concerned, this, the proton-proton interaction and the proton-neutron interaction is nearly the same. There is no difference. Okay. So if from the consideration of nuclear interaction, if I had a system of particles, say protons and neutrons at a very high energy, then they would keep on bombarding each other. So if I had a system of protons, there are protons here at some very high energy, and there are neutrons. And you know from kinetic theory that if these particles are free at some high temperature, they will just keep on whizzing around, moving around. And there is a probability that one proton will hit one neutron will hit one neutron, and one proton will hit a neutron. Okay. Now, so in this kind of a mixture, you are going to get helium as well as deuterium forming. And as far as the nuclear interaction is concerned, these are the interaction between the proton and neutron and proton is nearly the same. It doesn't matter if it's a neutron or a proton, as far as the nuclear interaction is concerned. But if a proton has to interact with a proton, it has to overcome the electrostatic repulsion. So the proton-proton reaction rate, or the reaction rate between two positive particles, will be reduced by this factor. Whereas the proton-neutron reaction rate, the neutron doesn't have to overcome the electrostatic potential. There is no electrostatic potential between the neutron and proton. Right? So the neutron doesn't have to tunnel to get to the proton, whereas one proton has to tunnel through the electrostatic potential to get here. So if I have the same number of protons incident on a proton, the reaction rate will be reduced by this factor compared to a situation where I have neutrons incident on the proton. Right? So these kinds of considerations are very important if you want to study any nuclear reaction. It is also important if you want to study, say, some tunneling in some condensed matter system, because the only situation which you can exactly analytically solve by and large is the step potential. And in reality you will not have a step potential, you will have some potential of some arbitrary shape. And if you want to study this, then you have to take into account the fact that the wavelength keeps on changing inside, and you have to, one way is to use the WKB approximation. So we have considered two applications of the WKB approximation. One is to find the bound states in a situation where we have a potential which has a kind of minima, and the energy is more than the value of the minima, but so we have a situation like this. We found the bound states, and if we have a situation like this, we calculated the transmission coefficient. So these are two applications of the WKB approximation. Which we have considered. So let me again recapitulate what is the WKB approximation before terminating. So the WKB approximation is as follows from this. Suppose I have a potential which is constant. If I have a potential which is constant, this is the constant potential V, and I have a particle whose energy is E, and I write down the stationary state solution phi x in this region as e to the power I phi x, then phi x we know is equal to the phase. Phi x is the phase of the wave function as we go from here to here. So this is 0 and this is some position here is x. So the phi x is the phase of the wave function as we go from here to here, and this we know in a situation where the potential is constant, we know this to be equal to p x by h cross, because the momentum inside is also constant, and the momentum inside we know it is 2m e minus v, right? Just the
What is the value behind these considerations? Psi x is equal to the power I phi x.
this we have actually solved this, right? We have solved the wave function, we have solved the Schrodinger equation in a situation where the potential is a constant. We have worked out the exact solution. It turns out to be a plane wave, and that plane wave I can just express in this fashion: e to the power I phi x, where phi x is the phase when I go from here to here, and phi x turns out to be p into x by h cross. This is the exact solution which we have obtained by solving the Schrodinger equation exactly in the region where the potential is a constant, right? This is nothing but the solution which we have worked out in this region, and phi x is the phase of the wave function which turns out to be px by h cross, and the momentum p is a constant inside. Now if the potential is not a constant but it is varying, now what happens? Now the momentum of the particle, so if I have a particle moving here classically, its momentum will be a function of the position. So in a varying potential, p is now a function of x, and this is equal to 2m e minus vx. So classically here the momentum was a constant, and the phase for the quantum wave function turned out to be e to the power I px by h cross, and p was a constant. Now if I have a potential which is varying continuously, then classically we know that the momentum of the particle is different as it goes from position to position. So in a situation where the momentum was a constant, in the first case the particle, the wave, this wave was a wave with a fixed wavelength, and it was like this. The wavelength remained unchanged because the wavelength is given by this p by h cross. This is a wave number. Okay. Now the potential is changing. So the momentum of the particle keeps on varying as we go along. So if you want to think of it in terms of the wavelength of the wave keeps on varying as we go along. And the wavelength is inversely proportional to the momentum. If you look at this, the wavelength, this is equal to 2 pi x by lambda. This is the wave e to the power I 2 pi x by lambda. So the wavelength is inversely proportional to the momentum. In a situation where the potential is varying continuously, the momentum of the particle changes. The wavelength is going to be shortest when the momentum is largest. In this situation we know that the momentum is largest somewhere near the bottom of the potential well. So the wavelength is going to be the shortest over here, and then as the particle goes up the potential, it keeps on losing kinetic energy, the momentum gets smaller and smaller, the wavelength has to get larger and larger. So the wavelength gets larger and larger as the particle moves up the potential well. And when it reaches the classical turning point, the wavelength becomes infinite because the momentum is 0. So over here, the wavelength is infinity. Okay, so you have a wave. If you want to think of the corresponding wave over for this situation where the momentum is changing with position, then the wavelength also changes as the momentum changes in the classical interpretation. Okay, and we want to calculate the phase. So in the situation where the potential was a constant, the phase was px. Now the momentum itself is a function of x. So if I want to calculate the phase from as I go across, then the phase will be, I can no longer write it as px, I have to integrate, so it will be from 0 to x p x prime dx prime 1 by h cross. So this is a kind of approximate solution which we are constructing, guided by the fact that the momentum keeps on changing as we go along the potential. The wavelength keeps on, which implies that the wavelength keeps on changing as we go along the potential, and we calculate the phase by integrating p dx, or the number of oscillations the wave function is going through. So where it is oscillating fast, the phase change is very fast. Here the momentum is large, the wavelength is small, and the phase change is very fast, p is large. In these regions, the phase change is very slow. So we are trying to get an approximate solution just using the fact that the momentum keeps on varying, classical momentum keeps on varying, and the classical momentum we are converting to the wavelength, and we just calculate the phase change as we go along. Now the phase change goes to 0 as we approach the classical turning points, because the momentum becomes 0. So this picture breaks down as we approach the classical turning point, because there is no change in phase. If I have this picture and I use this to calculate the phase, there is no change in phase as I approach the classical turning point. The wavelength becomes infinite. So I cannot think of this, the wave function, being described by a wave whose wavelength keeps on changing slowly as I move along. Okay. So this picture fails in these classical turning regions, turning points. This picture is quite valid over here, where the wavelength oscillates so fast that the potential doesn't change much across the wavelength. Okay. So this has been the WKB approximation. What remains to be understood still is how we match the solution, how do we connect the solution across the classical turning points. And this is something which I shall address after the mid-semester break. Okay, in the next class.